Hi everybody, in this video you're going to learn about the mean value theorem. So go to your notes and open up to the next spot where you're going to take these notes, title it mean value theorem. Before I talk about mean value theorem, the wording of the mean value theorem is somewhat similar to the intermediate value theorem. It definitely is very different than the intermediate value theorem, but the wording is somewhat similar here. So just as a reminder, since it's been a little bit since you've seen the intermediate value theorem, the intermediate value theorem says if I have a continuous function on an interval a, b, and I choose some w, some of you like to call it n, or some w between f of a and f of b, so w is a y value, then we know the intermediate value theorem guarantees there must be some c value within the interval AB such that f of c equals w. Basically, the intermediate value theorem says that every single y value in between f of a and f of b is hit. So you could pick any y value here and there's going to be an x value that goes with it. So that's the intermediate value theorem. The mean value theorem, where's my mouse? Here it is. The mean value theorem looks like this. First of all, in order to use a mean value theorem, there's a couple of things you have to have with your function. Your function needs to be continuous, meaning there's no holes, gaps, asymptotes, or jumps, and it needs to be differentiable. That means you can take the derivative anywhere. So there's no sharp points, no cusps, no vertical tangent lines. To build up the mean value theorem, I'm going to have you draw this picture. So pause the video and draw a little graphing grid. Don't make it too little though. And make it accurate so that the x values agree and the y values agree. You're going to put a at a y value of 2 and make b have a y value of 6. So pause right now and set this up. So this is what the mean value theorem says. I'm going to draw a function from a to b. Now a and b, these points here are the endpoints of my function. And draw yourself a function that looks like this. It's going from a to b, so these are the endpoints. Because my function is differentiable and is continuous, the mean value theorem guarantees that I'm going to have at least one x value, I'll call it c, in between a and b, such that the derivative at that c value is equal to the slope of AB. Now, AB is really a secant line. I'm going to visualize or draw what I just said here. This is a secant line from A to B. And we're going to use spaghetti in class to help visualize this more. But imagine rolling the secant line up towards the function and picture points on the function that would have a tangent line equal to the secant line. So as I'm going up this way, right around here, I would have a tangent line equal in slope to the secant line. As I keep moving up right around here and right around here. So you're going to want to label these points here with a star. These are the x values that have a tangent line that's equal to the secant line, meaning they have the same slope. The mean value theorem guarantees that there's at least one of those points. Here I have 3 of those points, but I'm going to have at least one. Now, so that the definition makes sense, let's just think what a slope of a secant line is. Slope of a secant line is just y2 minus y1 over x2 minus x1. So that would be f of b minus f of a all over b minus a. And we know that at some c value, the slope of the tangent line is equal to this slope. Well, slope of a tangent line is just derivative, or f prime. So this is what it says. There is going to be at least, where am I here? There we go. At least one x value where the derivative at that x value, which I'm going to call c, is equal to the slope of the tangent line. That's what the mean value theorem says, basically. So you're going to want to put a box around this. And hopefully the picture helps. We're going to do this again in class with spaghetti, so it really makes sense. But again, from the endpoints a to b, whatever that secant line is, there's at least one spot on the function where the tangent line is the same as the secant line. So here is a more formal definition of the mean value theorem, so you're going to want to pause the video and write this down. Suppose f is continuous on the closed interval, differentiable on the open interval. There is some x value c within this x interval AB such that the derivative at that one c value or that one point is equal to the slope of the tangent line. Now there's something called Rolle's theorem. It's the same exact thing as the mean value theorem, same wording. The only differences for Rolle's theorem's picture is here. The height of A and B, or the y values, is the exact same. Notice before in my picture, the heights of the endpoints were definitely not the same. For Rolle's theorem, the heights of A and B are the same. So that means if you draw a secant line from A to B, it's going to be horizontal. The slope of a horizontal line is 0. So you know that the slope of the secant line is 0, and there's going to be at least one point from A to B as you move along your curve, such that the tangent line, slope of the tangent line, I should say, or the derivative is flat, is 0. So draw that, make sure you have those definitions down. I'm going to end with one example here for your notes. We're going to do examples like this in class on Monday to make sure you understand everything. Where am I? Okay, this is the last page of the notes, this one example here. I'm going to give you a function, it's a quadratic, x minus 2 squared plus 1. I'm telling you it's on the closed interval 1, 4, and I want to find what x values within, so this c value or c values are going to be within 1, 4. They need to satisfy the mean value theorem, and I want to have this visual in my notes to help me see that my c value makes sense. So first we have to identify all the parts of the mean value theorem. We have our endpoints, the heights at the endpoints, we have our special c value, and we have the tangent line's slope or the derivative at that c value. Well, the endpoints are pretty easy to pick out. They're just these guys right here, 1 and 4. F of A and F of B aren't too bad either. That's right here. I'm just going to evaluate my original function at A, at B. As you write this down, make sure you understand that I'm plugging into my function and I'm getting heights. So far, we can do a pretty good diagram just to see what's going on. Notice that this is a quadratic in vertex form. So my vertex is right 2, up 1. So this thing right here is the vertex. And I go left 1, up 1, right 1, up 1, right 2, up 4. So this is a pretty accurate graph. I stop at 1 and at 4. To use the mean value theorem, we have our endpoints 1 and 4. This is the slope of the secant line. So this red thing right here, the slope of it is f of b minus f of a, all over b minus a. I want some c value in between 1 and 4 that has the same slope as my secant line. So some tangent line. I can kind of see it's going to be around there. That's the only point that would have the same slope as my secant line. But let's do the math to picture or to find out exactly where that's going to be. Let's actually do, oops, here I am, f of b minus f of a, all over b minus a. So write this work down so when you're in class on Monday or Tuesday, you can do this as well. F of b I found out was 5, f of a was 2, all over b minus a, 4 minus 1. That is 3 over 3, or just 1. So 1 is the slope of my secant line. 1 is also what I want f prime of c to be. So I want some tangent line on my curve to also have a slope of 1. That's our goal slope. So we're guaranteed that somewhere in 1 to 4 that the function has a tangent line with a slope of 1. We just need to find out where. So again, we want the derivative or the slope of the tangent line to be 1. So why don't we find the derivative? So 2 times x minus 2 to the first power plus 0. That is 2x minus 4. I want my derivative, which is the slope of the tangent line, to equal 1. So just set it equal to 1 and solve. I'm going to add 4 to each side. Divide by 2. X equals 5 over 2, or 2.5. So the mean value says that this is the c value. So let me go to 2.5. I'll do it in blue. Here's 2.5. The mean value theorem says right here, if you go up, that's the x value where the tangent line, wow, that's bad. The derivative of the function here, or the slope of the tangent line, will be the slope of the secant line. And if you drew your graph relatively accurately, it should look like they are the same slope. They're basically going to be parallel right there. So we'll practice this in class next time I see you with a worksheet. Have a great rest of your weekend.